In this series, the next topic is blackbody radiation heat exchange. We know the concept of blackbody, what is blackbody, and now we want to find the equation for radiation heat exchange between the blackbody. In radiation heat exchange, there are number of reflections and absorptions which are taking place. But in case of blackbody, reflections will be 0, means R will be equal to 0. Reflectivity of the black bodies will be equal to 0. All energy will be absorbed. What we can say about the emission, the energy leaving the surface will be in the form of emission. Now consider two surfaces, let's say surface 1 and surface 2. They are taking part in radiation heat exchange. With the concept of emissive power, with the concept of shape factor, we can write down the equation into the form of Q12. What is the meaning of Q12? Q12 is the energy leaving the surface 1 and reaches the surface 2. Energy leaving the surface 1 and reaches surface 2 will be equal to A1 F12 EB1, where A1 is the surface area of surface 1 and F122 is the shape factor of surface 1 with respect to surface 2, and EB1 is the emissive power of this surface 1. Similarly, we can write down the equation when we are considering surface 2 is emitting energy and that energy is received by surface 1. For that case, Q21 will be the energy radiated by surface 1, out of which energy 1 will receive some amount of energy, that will be Q21. It will be equal to A2 F21 EB2. When we will put the value of EB1 and EB2, emissive power of surface 1 and emissive power of surface 2, the equation will be in the form of temperature T1 and temperature T2, where T1 is the temperature of surface 1 and T2 is the temperature of surface 2. What will be net radiation heat exchange? Net radiation heat exchange will be calculated by the difference of these two equations, equation 1 and equation 2. We will put the value of these two quantities, which is Q12 and Q21, from these two equations, equation 1 and equation 2, and we will get the final equation. In the final equation, we are going to use the concept of reciprocity rule or reciprocity theorem, in which we can find the value of shape factor of surface 1 with respect to 2 with the help of shape factor of surface 2 with respect to surface 1. Okay. And the next topic is radiation heat exchange between non-black surfaces. We have done the radiation heat exchange between black surfaces and it is very simple. What we will do when we are interested to find the radiation heat exchange between non-black surfaces. To understand, to derive the relation for radiation heat exchange between non-black surfaces, first we will understand, we are going to introduce two more terms, irradiation and radiosity. What is irradiation and what is radiosity? The symbol for irradiation is G and the symbol for radiosity is J. Consider an arbitrary body, any body which is at temperature T. We are going to assume some amount of energy is falling on it. Some amount of energy is falling on it and it is represented by, let's say, capital G. Due to its temperature, there will be some emission. There will be some emission of energy from the body. From the energy which is falling on the body, some amount of energy is reflected. If R is the reflectivity, the energy, amount of energy which is reflected will be equal to R multiplied by G. Energy emitted by the body, let's say it is E. Energy emitted by the body, it will be E. Now irradiation. Irradiation is the amount of energy falling on the body, or we can say irradiation is the amount of energy coming towards the surface. Energy coming towards the surface is G and it is known as irradiation. What is radiosity? Radiosity is the total amount of energy leaving the surface. This is our body or surface. What are the various forms of energy leaving the surface? It is E and rho g, Rg. So radiosity is the sum of, in this case, radiosity is the sum of two energies E and Rg. It means it is the sum of energy emitted by the body and energy reflected by the body. Let us consider a surface upon which some amount of energy G, which is irradiation, is falling on it, and some amount of energy is leaving the surface, which is radiosity. It is represented by J. The net radiation heat exchange by this surface can be represented by Q, and it is due to G and J due to irradiation and radiosity. If we have assumed the epsilon is the emissivity of the surface, and we have assumed there is a reflection from the amount of energy received by the surface, then we can say the reflected amount of energy is R multiplied by G, and emission from the surface is in the form of emissivity multiplied by emissive power of black body. Before the start of the derivation, we have to assume few assumptions for the simplification. First one is we will assume the surface is an opaque surface. The surface will be opaque surface if the transmissivity of the surface is equal to 0. The second assumption is the surface is a diffuse surface. The surface is said to be a diffuse surface if its properties are independent of direction. A surface is said to be a gray surface if its properties are independent of wavelength. We will also assume that the surface is an isothermal surface, and these quantities, irradiation and radiosity, they are uniform. Net radiation heat exchange or net radiation leaving the surface, let's say it is Q, and it is due to J and G. Its equation will be in the form of area multiplied by difference of J and G, where J is the radiosity, which is the sum of two form of energy, emissivity multiplied by EB plus rho, or we can say Rg. The equation of with the help of electrical analogy to Ohm's law resistance. By using the electrical analogy, we can say that there will be some sort of resistance. That resistance is a surface resistance on the non-black surface. Now for the opaque surface. For the opaque surface, transmissivity is equal to 0. We have assumed the surface is opaque. Tau is equal to 0. By using this equation, we know this equation. Reflectivity will be equal to 1 minus emissivity. We are interested in the equation for net heat flow from the surface, which is due to radiosity and irradiation, which is due to J and G. We know we can find the value of J and G, and we can put the value of J and G in this equation. J, which is the radiosity, is the sum of two form of energy. It is the summation of two form of energy. The final equation for the net heat leaving the surface is in the form of area, emissive power of black body, and radiosity. By electrical analogy, we can compare these two equation given by Ohm's and heat flow equation. By comparing these two equations, we can say that there is a surface resistance. There is a surface resistance which is available in the denominator. This surface equation is the equation for this. This is the equation for surface resistance, which is in the form of emissivity, or we can say that every non-black surface have some surface resistance, and that is due to its emissivity. We can also represent the surface resistance on the electrical network if it is a surface from which we are going to assume there is a radiation heat exchange, or there is a net flow of heat, which is Q. It can be represented with the electrical circuit having some surface resistance. That surface resistance is 1 minus emissivity divided by area multiplied by divided by emissivity. Now two situation may possible. Either EB may be greater than J, or EB, emissive power of black body, may be less than J. If EB is greater than J, this is the situation. If EB is greater than J, we can say it will be a flow of heat to the surface. If EB is less than J, hence a negative value of Q will indicate the heat flow to the surface. And we can say that if emissivity is equal to 1, this is the case when the body is a black body, emissivity of a black body will be equal to 1. For that case, J will be equal to EB. J will become EB. Therefore, the net flow of heat from the black surface at thermal equilibrium will be 0. Net heat flow from the surface at thermal equilibrium will be equal to 0. Now let us consider two surfaces, surface 1 and surface 2. They are taking part in radiation heat exchange. Both surfaces are gray surface or non-black surfaces. As per the assumptions, we have assumed the surfaces are opaque, diffuse and gray. Let's say A1 is the area, T1 is the temperature, and epsilon 1 is the emissivity of surface 1. Similarly, we can assume other parameters A2, T2 and emissivity 2 for the surface 2. Fraction of energy leaving the surface 1, fraction of energy leaving the surface 1 and reaches to surface 2 will be A1 J1 F12. Fraction of energy leaving the surface 2, fraction of energy leaving the surface 2 and reaches surface 1 will be equal to A2 J2 F21. Net radiation heat exchange. Net radiation heat exchange, let's say it is Q12, it will be equal to the difference of these two equations, A1 F12 minus A2 F21. After rearranging the equation for net radiation heat exchange Q12 will be in the form of radiosity 1 and radiosity 2. Again, by electrical analogy, when we will compare the equation Q12 with the Ohm's equation, we can say that there is another type of resistance which is known as space resistance. The space resistance will be 1 by A1 F12. Thermal network between the two surfaces in steady state condition. The complete thermal network for the two surfaces can be drawn. And the maximum thermal potential will be due to EB1 and EB2. In between there will be two radiosity J1 and J2. On the one side there will be surface 1, on the other side there will be surface 2. Due to those two surfaces there will be surface resistances. Here there will be surface 1 having resistance. On the other side there will be a second surface having the second surface resistance. And in between the two surfaces there will be a space, and due to that space there will be a space resistance which we know that is a 1 by A1 F122. Now we can write down the equation for steady state radiation heat transfer rate between the two surfaces. Let's say it is Q. It is in the form of overall thermal potential divided by total resistances. Overall thermal potential means the thermal potential due to EB1 and EB2. We will write down here overall thermal potential divided by total resistances. In this case, how many resistances are there? There are three resistances. One is the surface resistance of surface 1, second is the surface resistance of surface 2, and in between there is a space resistance. We can say this is the first surface resistance, space resistance, and third one is the again surface resistance due to the surface 2. It is our overall equation for heat flow. We can consider the first case, the case of infinite long parallel planes. What is the meaning of it? If those two surfaces, they are plane surface and they are infinitely long and they are parallel planes. Let's say it is a surface 1 and surface 2. The view factor, shape factor will be unity in this case. Energy radiated by surface 1 will be intercepted by surface 2. The total amount of energy will be received by surface 2. In this case, the area of surface 1 and surface 2, area A1 will be equal to area A, and this equation, the equation for heat flow, will take the form of area, Stephen Boltzmann constant, temperature T1 raised to power 4, T2 raised to power 4 divided by this quantity. The second case is the case of two infinitely long concentric cylinder. If there is a case of two concentric cylinder and they are infinitely long, in that case, let's say these are the two surfaces, surface 1 and surface 2. It is surface 1 and it is surface 2. The view factor in this case, which is a shape factor, F122 will be unity, its value will be equal to 1, and area A1 is not equal to area A2, and equation will take, radiation heat exchange equation will take the form of Q will be equal to area 1